Hi, everyone. I'm Andy Miller, and this is a brief overview of our paper Model-Based Metrics, work done with Leon Gaddis, Joe Futoma, and Emily Fox. So the motivation for this work is that machine learning models should work well for everyone. And a key part of ensuring that is to measure performance using test metrics such as the area under the ROC curve, or AUC, to understand where the model succeeds and fails and what the consequences of deployment may be. So consider a sample across subpopulations defined by two variables, skin type and age. So typically we compute evaluation metrics such as the AUC on the entire population with relatively small uncertainty. But we may also care about AUC within subpopulations. And this idea introduces a new challenge. Each subpopulation by definition has way less data, which implies noisier estimates of metrics like the AUC. And this uncertainty will affect the smaller subpopulations the most. And this is a problem we see in health all the time. The size of subpopulations can vary widely. Consider the National Health and Nutrition Examination Survey population. If we divide the sample into age and ethnicity bins, some subpopulations are over 15 times as large as others. So how do we improve upon the typical subsample estimator? Well, first we observe that restricting to a subsample may throw away information, and partially pooling information from related subpopulations could improve estimates. So our idea is to introduce an evaluation model and form model-based estimates of performance metrics. This allows related observations to inform subpopulation metric estimates, and we recommend a procedure for specifying, fitting, and validating these evaluation models. So how does this work practically? Evaluation metrics like the area under the ROC or positive predictive value correspond to functionals of the conditional distribution of the prediction model's score, S, given outcome Y and subpopulation A. And typically we use the empirical sample from these conditional distributions to estimate this quantity. But again, when a subpopulation is small, the estimate will be uncertain. So we introduce these evaluation models that directly describe the conditional distribution of S given Y and A and potentially additional covariates X using evaluation model parameters lambda, shown here on the right. And we describe a procedure to specify, fit, and validate these models, and also to form a Bayes estimate of the metric, such as AUC or PPV, using the posterior predictive distribution. And we incorporate frequentist estimate uncertainty using an efficient approximation to the bootstrap. And in our experiments, we focus on multi-level regression models fit with Markov chain Monte Carlo. So we run experiments in two settings, one simulation study using statistics from the NHANES sample, and one semi-synthetic experiment using a rehospitalization prediction task. In the simulation study, we observe MBMs nearly always match or improve estimator accuracy over a range of problem and model complexities. And in the rehospitalization prediction task, we show that the improvement in estimator accuracy is typically the greatest for smaller sample sizes. So to conclude, subsample-based estimates are noisier for smaller subpopulations, frustrating accurate model evaluation. And introducing an evaluation model can improve accuracy, and we can think of this as exploring the bias variance trade-off. We also observe a bigger improvement in smaller subpopulations. And lastly, it's important to note that there is no substitute for more and better data. All models require assumptions, and the typical subsample estimators are consistent and work well with enough data. So thanks for listening.